Well, going logically through our cases, now we turn to the case of a strong base added to a weak acid. And when we add that strong base, we know that we're going to be left with an excess of the hydroxide anion and a concentration of the conjugate base, which is the acetate anion. So let's write down the reaction. And again, we're going to use the Rice table to do this calculation. And so we always begin a Rice table with the reaction. And in this case, we've got the reaction of the anion produced in the reaction of the weak acid, and that reacts with water to form our OH minus plus the concentration of the weak acid. We generated that by, again, adding a strong base to a weak acid. So our initial concentration before any reaction has taken place is that we have some concentration of that anion, the acetate anion, and before the reaction takes place, of course, we have no product formed on the right-hand side. Now the change, the C in Rice, is going to be some removal of that anion resulting from the reaction of water with it, producing an equal amount of the OH minus and the acetic acid molecule. At equilibrium, we now have the ability to write down the concentration of the anion, that's C minus X, and the concentration of the OH minus and the acetic acid is identically X. But now, as we did in the case of adding a weak acid, we have an initial concentration of the acetate, the 10th molar, but it doesn't matter how that acetate was formed. We could have added sodium acetate, CH3COO, to the water, or we could have added the strong base. The strong base is NaOH. We would come out with exactly the same result. But at equilibrium, the equilibrium constant isn't K sub A for the acid, as it was in the first case, but it's a base dissociation constant, K sub B, and that's equal to the autoionization of water, K sub W, divided by the acid dissociation constant, because we have an acid and its conjugate base. And anytime we have that, we know that K sub W is the product of Ka and Kb, and therefore I can solve for the base dissociation constant, but I can also write down what the concentrations are in terms of that equilibrium constant. So I just come back to my reaction in the Rice table, and I can immediately write down that the equilibrium constant is equal to the product of the concentration of OH minus and our acetic acid concentration divided by the reactant, which is CH3COO anion. And I can also put in the numbers for the acid dissociation constant. Remember, that was 1.76 times 10 to the minus 5, and my autoionization of water is 1 times 10 to the minus 14. So I can insert that into the expression and immediately calculate the appropriate equilibrium constant for this, which is equal to 5.7 times 10 to the minus 10. Again, at small, it means that the reaction has gone only slightly to the right, and when the equilibrium is established, we have only a small fraction of that acetate anion being converted back to OH plus and the acetic acid molecule. So now we come to the quantitative analysis of this. And the first point is that we've calculated our equilibrium constant for this reaction. That equilibrium constant is small, but it's still much greater than the autoionization of water. And that means that even though that equilibrium constant is small, it's 50,000 times larger than the dissociation of water. And this is a reflection of the strong basic character of this conjugate base. It means that we can complete effectively extracting an H plus from water to form OH minus. But now we can solve the problem quantitatively by inserting the equilibrium concentrations from our Rice table. So we pull up from our Rice table the fact that the equilibrium constant for this is equal to our concentrations on the right-hand side, that is OH minus and the acetic acid concentration, divided by the concentration of the acetate anion, which is 0.1 minus X. Well, when we see this and we recognize that the equilibrium constant, 5.7 times 10 to the minus 10, is small, that suggests that we use the same approximation as we did before. That is that X is small compared to 0.1. And so rather than having a quadratic equation to solve, we can solve our equilibrium constant by simply writing that X squared is equal to 5.7 times 10 to the minus 10, and then we will approximate this not as 0.1 minus X, but ignoring X with respect to 0.1. That leaves a 0.1 in the denominator, and that means that I have 5.7 10 to the minus 10 times 0.1, which is equal to 5.7 times 10 to the minus 11. And that gives us X, which is a calculation of the concentration of the hydroxide anion, and that turns out, when we take the square root of 5.7 10 to the minus 11, we have 7.5 times 10 to the minus 6 molar. All right, so now we've calculated the OH negative ion concentration, but we also know, again, that the product of that OH anion and H3O plus cation is always 10 to the minus 14. So that means we can immediately solve for H3O plus in this solution, and that's equal to the autoionization equilibrium constant for water divided by our 7.5 times 10 to the minus 6. And that gives us an H3O plus concentration of 1.33 times 10 to the minus 9. But we want pH. And so we know now exactly how we're going to calculate the pH. That's minus log to the base 10 of the H3O plus concentration. So I have minus log to the base 10 of 1.33 times 10 to the minus 9. And that gives me a pH for that mixture of 8.88. And of course, a neutral solution has a pH of 7, so this is clearly a basic solution. The pH is increased from 7 to 8.88.